So today we are starting one of the last topics of Unit 2. We're going to talk about measurement. And of course, as you can imagine, when we get into our dosage calculations in the next unit, measurement is a big deal. Having the appropriate units, making appropriate conversions, and of course knowing what you're going to use to administer the medication is extremely important in order to make sure you get dosages accurate and correct. So today we're going to talk about some of the units and a little bit about how we convert from one unit to another. So we're going to start out talking about standard or customary units. We changed over to that name of customary because they really aren't standard. In fact, our metric system is now considered more of a standard than what the old customary units were. Part of the reason for that was customary units were never meant to be a measuring system. Each unit was developed to meet a specific need and without any thought of ever using them together. So we're start talking about units of length. So for units of length, the reason measurement came about was for a need to communicate. So let's say we're both building a table or whatever, and we want them to be identical. We're going to each build one and we want them to be the same. Well, if we're in the same room, that's easy. We can just walk over next to each other, mark them off, make sure they're the same size. But if you're down the hall or across town or however, there needs to be some way to communicate that. Well, I could always say, let's say that our piece needs to be the size of this piece of paper. Well, I could take my pen and I could go, well, it's 1, 2, just over 2 pens in length. Well, then it comes to you and you take your pen and you go 1, 2, yours ends up being significantly larger than mine. The reason being, all the pens we used, I'll pick them up, were much different size. So for measurement to work, both people had to have the device and they had to be pretty much the same size. So in order to communicate that information, we had to have that qualification. Both people had to have them, had to be close to the same size. But it also then had to stand the test of time because another need for measurement was to keep records. Let's say we're building this table now, but we know that in another year we want to come back and build another one that's the same. Well, we need to record what we did this time so that when we come back to do it again, we make sure we do it the same way. And so we want to make sure that what we used to measure today is something that's going to be available in the future whenever we needed to look back on those records. And those are really the two biggest reasons for needing measurement. And then, of course, a third one came about as economic growth occurred, and that is to trade. You need some way to measure how much you're giving back and forth to make sure you're coming out fairly in any sort of trade or commerce. Let's talk about length. As we mentioned, to measure lengths, both people had to have one of the objects, each of the objects, and they had to be close to the same size. Well, when it came to length, they tended to use parts of the body. And because people were, on average, much smaller back at that point, there was less variation from one person to the next. So starting out with what we're used to as our smallest unit of length in the customary system, the inch. The inch was from the point of the first knuckle to the tip of the thumb. So I could measure my piece of paper, 1, 2, 3, 4, and count on up. By the way, the motion of me you saw me rolling my thumb just a little bit as I moved it up, which is natural tendency. That's where the inchworm got its name because it tends to move in that same rolling motion. Well, bigger than an inch, the unit we're most used to is a foot. And of course, 1 foot is 12 inches. And the foot is exactly what it sounds like, from the back of the heel to the tip of the longest toe. Now, there were other units in here that were used a lot that have kind of disappeared on us. And the reason they disappeared was because in the 500s or so, King Edward declared his thumb and his foot and his everything else were going to be the official measuring units of the land, of his kingdom. Well, this was an egotistical move on his part, but it was very important to allowing future advances in measurement. One of them is, if you think about if I'm going to measure the height of this wall behind me here, well, I'm not going to measure in inches. I'm not going to take my thumbs and creep all the way up that wall measuring with my thumbs. We would probably measure it in feet. The problem is I could maybe get up to about here with some serious stretching, but I'm not getting my foot all the way up to the top of that wall. A foot was used for measuring things along the ground because that's where feet are. To measure heights like that, a foot didn't work. So they had a unit called the hand. A hand was the width of the hand where the fingers meet the palm, and you stack the hands to measure vertical distances. Because King Edward declared that his thumb and his foot were now the official measurements of the land, craftsmen came in, they measured his hand and his thumb and his foot and whatever, and they cut blocks of wood that size. Well, now we no longer needed to get my foot to the top of the wall to measure it. I had that block of wood that I could use. So it eliminated the need for some of those extraneous units like that. It also opened up then the advancement to creating a ruler where they took a big stick and just marked off those lengths on that big stick because now they were standardized. Bigger than a foot. There are lots of other units that came in there as well. One of them was a cubit. Cubit was from the tip of the longest finger to the point of the elbow. That was about 16 inches. This was your carpenter's, builder's unit. Everything in carpentry was spaced 16 inches approximately. Floor joists, wall studs. You just stuck your arm in there, put the next one up against it, and nailed it in place. And that was your spacing. Well, bigger units that we actually used, the yard. And of course, we're used to a yard being 3 feet. Most people think of a yard as the length of a person's stride, and it is approximately a yard, but that's not where it came from. A yard came from either the point of your chest or the tip of your nose to the end of your outstretched arm. It was a tailor's unit. It was used for measuring fabric. So the tailor would grab the fabric, pull them out, count 1, 2, those were yards. And of course, King Edward declared his yard to be the official unit of the land. Now, King Edward's foot did not have 12 of his inches. His yard did not have exactly 3 of his feet. A couple hundred years later, these units were adjusted so that there was a conversion between them. Up until that point, there was no conversion. If you were to measure something in inches and I measured something else in feet, there was no way to compare the size between them because there was no conversion. One of us was going to have to go back and remeasure in the other unit. Now, bigger than the yard, there is a unit that we'll talk about called a rod. A rod contains either 5.5 yards or 16.5 feet. It was a shepherd's tool. It was used for measuring. The shepherd had 2 tools. One was the staff, which was that hook that you see little Bo Peep holding. It was for hooking the animals around the neck to shear the wool, whatever. The rod was just a big stick. It was a defensive weapon. And it was basically, it came into pasturing the sheep, or keep the sheep straight. We would lay out, you're going to keep your sheep over here, I'll keep my sheep over here. We have some landmark, like a big rock. And in order to make sure it's fair, I put my rod on the ground, you take your rod, put it end to end, and we count. 1, 2, and just keep grabbing the rods and flipping them end to end. That was the beginning of land measurement. And to this day, if you look at surveys for land, most surveys are done in rods and another unit called a chain, which is 66 feet, 4 rods. That's how land was laid out. That's how the official description of land is still done. Bigger than a rod, bigger than a yard. Again, there are other units in there like a furlong or and several other units. We're going to jump up to a mile. 1 mile was 5,280 feet, or 1,760 yards. A mile, so I've seen a few different theories as to where the mile came from. The one that I've seen that makes the most sense is from Greek and Roman military. It was a pace was starting on your left foot, going to the right and back to the left. It was the distance that soldiers marched in formation 1,000 paces, which makes sense. That'd be about 5,280 miles. Well, like I said, these units were never intended to work together. Each one of them was developed for a different purpose. The hand was developed for measuring heights because feet didn't go up and down, and inches, the thumb, were too small. Still used in some special applications today, like measuring height of livestock. They were never intended to work together. It was several hundreds of years later that they were adapted and forced to work together in a system. So because of that awkwardness, and also the fact that King Edward made the declaration, other kings and other rulers in other parts of the world made similar declarations. So the yard was very different from one area to the next, and all the units were very different from one region to the next. They were definitely anything but standard. In the metric system, they decided to fix this, and it actually happened in the 1880s, and we developed the metric system. And the metric system was developed in order to eliminate a lot of these issues, these weird conversions, like 3 feet in a yard or 12 inches in a foot. But they also knew that there were things that worked very well, so they wanted to keep those involved. We're going to come back and we're going to do the metric system for each type of unit later, just because it kind of all fits together in one big system. If I want to convert units, well, most of us know if I tell you I have 3 feet and I ask for inches, most of you could probably just yell out rather quickly 36 inches and 3 feet. Because you've used them enough, you know there's 12 inches in a foot, you just multiply by 12. But if you didn't know that, you would take the 3 feet, put it over 1, and then use a conversion factor. This conversion factor is a unity fraction. Remember, a unity fraction is a fraction where the numerator is equal to the denominator. Well, any equivalency will give us that. What's an equivalency? Well, equivalency is what we just put up above. 12 inches equals 1 foot. That's an equivalency. 3 feet equals 1 yard. That's an equivalency. So here, what I'm going to put in here, I'm going to put 1 foot equals 12 inches. Now, it doesn't look like they're the same, but they are. 12 inches and 1 foot represent the same value. There's 2 different ways of representing it, so they look different, but they are still the same value. So that does still equal 1. Now, how did I know to put the feet on bottom and the inches on top? Well, because I want to get rid of feet. So to make them cross cancel when I multiply my fractions, they were on top, I put feet on bottom so that they cancel out. Now I have 3 times 12 inches is 36 inches. 1 times 1 is 1. So 36 inches divided by 1 is just the 36 inches. Well, as we mentioned, we didn't need to do that there because we could convert feet to inches without using that conversion factor. This process here, by the way, is called dimensional analysis. And it's really the first example that we've had in this course, by far from the last. Dimensional analysis is going to be the most powerful tool we have for doing dosage calculations in Unit 3. So anyway, let's look at a conversion here that we might not be as familiar with. Let's take 99 feet and let's convert it into rods. That's one of the reasons I included rods in our length, even though it's not a big deal in medicine. is because it's a conversion that you can't do off the top of your head for most people. So we take our 99 feet and we're going to put it in fraction form by putting it over 1. This is a common trick for doing conversions. Also, for most of our dosage calculations, we're going to do something similar for a lot of it. And then we're getting rid of feet. So feet are on top. I'm going to put feet on bottom so they cancel out. And I'm converting those feet into rods. So put rods on top. My equivalency here is 1 rod is 16.5 feet. So again, this is a unity fraction because the numerator and the denominator represent the same value just in different ways. Now, my feet cross cancel out. On top, I have 99 times 1 rod is 99 rods. On bottom, 1 times 16.5 is 16.5. And then we divide it out. 99 rods divided by 16.5 is just 6 rods. So 99 feet is 6 rods. Well, let's look at some other units. Let's talk about weight and mass. Before we talk about the units, we need to talk a little bit about the difference between weight and mass. The difference really is slight difference in what they measure, but the big difference is how it is measured. Weight is the force of gravity on an object. Mass is the amount of matter in the object. So matter is like the amount of particles, the amount of atoms that are in the object. And again, the big difference is how they're measured. Weight is measured using a scale. And a scale is a precision spring. A spring, if you have a good spring, the amount that spring stretches is very, very specifically related to the amount of force that you put on it. So a scale takes one of those good springs, puts it in a frame of some sort with an indicator mounted on it. So that if you put a weight on here, that indicator moves. There's where that indicator moves to. There's a scale here, some sort of markings that indicate where it started and how far it moved to. And so you can just read off of those markings then how far the spring has stretched, and also then what the weight is, what the force is on that spring. So that is how weight is measured. Mass is measured using a device called a balance. And a balance is like a really precision teeter-totter, if you want to think of it that way, on a smaller scale. So you put the object we're trying to measure on one side, then we put known masses on the other side. And when they balance, whatever this known mass is, that's the mass of our object that we're trying to measure. Now, if you look at those, you think, well, both of those are measuring the same thing. And, well, they're measuring things that are related. One is going to affect the other. The more mass an object has, the more it's going to weigh, because the more gravity is going to pull on it. But the difference is mass is not dependent on gravity. Well, what does that mean? Well, let's say we go to the moon. On the moon, gravity is 1/6 of what it is on Earth. Well, in our scale, that means it's going to pull 1/6 of the distance, so the weight is going to be 1/6 of what it was on Earth. For the balance, yeah, the amount that gravity pulls on our object changes, but the amount that it pulls on the known mass changes as well. So the mass of the object stays the same. With that all said, let's get to the units. In our standard system, we tend to focus on weight. I'm going to start out with mass. Our standard unit of mass is called a slug. Now, a slug is the mass that on Earth would weigh about 32 pounds. So it's a rather large unit. And most of you have probably heard the slug used, but didn't realize it was an actual measurement unit. A lot of people will say that there's a slug of them, just meaning there's a large amount of them, because the slug is a rather large unit. As we said, in the standard system, we tend to focus on weight. So let's talk about weight. We're going to start from the large units and go down to the small. Talking about a ton. Well, most of us know that a ton is 2,000 pounds. This is mostly true. Most tons are 2,000 pounds. This is actually what is referred to as a short or a net ton. What does that mean? Well, it's just like a net and gross paycheck. The ton was originally used for buying and selling grain. So you couldn't put a ton of grain on a scale. It had to be in a container. So a gross ton was the grain plus the container, which is obviously going to be larger. The net ton was 2,000 pounds. I'm not going to put the gross ton up here because I don't want you to get confused with it because it is a different number. Just be aware that there is a difference between a net ton and a gross ton. Now, the abbreviation for pound, it would have made sense for pound to be abbreviated PD. However, in the bookkeeping system for buying and selling grain, PD was already used for the abbreviation for paid. They didn't want to make any confusion there, so they decided to use the Latin word for pound, which is libra. So that's where the LV came from. Smaller than a pound? 1 pound contains 16 ounces. Well, for ounces, since we use the Latin word libra for pounds, they decided to use the Latin word for ounces as well, which is ounza. That's where the OZ comes from to abbreviate ounces. There are units in our standard system that are smaller than an ounce. One is a dram. There are 16 drams in an ounce. Now, I should specify these are dry drams. There are wet drams as well, which is slightly different, which is frustrating because it gets confusing. But there are 16 drams in an ounce. Smaller yet, we have minimums. 1 dram contains 60 minimums. Think of a minim like a minute, 60 minutes in an hour, 60 minimums in a dram. A dram was one of those apothecary units used for measuring medications. A minim was much smaller for measuring smaller amounts of medications. Then there was also another unit that became almost indisposable, and that was the grain. There are 7,000 grains in 1 pound. I don't know why they always go grains up to pounds instead of going to drams or minims or ounces, but 7,000 grains in a pound. Those of you that are into shooting sports, gunpowder, bullets, stuff like that, grains is a common use there. Grains, and you should be careful with this one, grain is abbreviated GR. In the metric system, we're going to have grams, which is just abbreviated with G, so we have to be very careful not to mistake those two. Grains were so important in the measurement of medications and medicine that it was actually absorbed into the metric system for medical purposes in order to keep using it. Unfortunately, that absorption was kind of sloppy. Didn't make it very clear. Next, let's talk about the difference between volume and capacity. Well, volume was derived from length units. And actually, in most cases, calculated from length units. For example, if you had a box that was 14 inches by 10 inches by 6 inches high, the volume was just 14 inches times 10 inches times 6 inches, otherwise known as 840 cubic inches. You'll notice here that the unit is a length unit cubed. Get that cubed out. So it is derived from length units. That's all volume is calculated from length. Capacity is standard size containers. So starting off with one of the larger ones, as far as medicine is concerned, a gallon. A gallon actually was the size of what was held in a standard men's hat. Smaller than a gallon, you have a quart. And a gallon holds 4 quarts. A quart is actually shortened from the phrase quarter gallon. Smaller than a quart, we have a pint. Quart contains 2 pints. A pint was a standard size jar used for serving beverages or for preserving fruits, vegetables, and stuff like that. It was liquid measure. A gallon could be either dry or liquid. And yes, there is actually a difference between a dry gallon and a liquid gallon. But we have kind of overlooked that difference and absorbed them into one as history. Smaller than a pint. 1 pint contains 2 cups. A cup comes from your hand. It was a baker's unit, and it was dry measure for powdered things like flour, sugar, salt. You would hold your cup and you dump the flour and whatever you could hold heaped up in your cupped hand. That was 1 cup. Smaller than a cup, you have fluid ounces. 1 cup contains 8 fluid ounces. Smaller than a fluid ounce. 1 fluid ounce contains 2 tablespoons. And smaller than a tablespoon. 1 tablespoon contains 3 teaspoons. I'm always very careful, by the way, to write tablespoons with a capital T and teaspoons with a small t, because in many cases, that's the abbreviation that's used for them, just capital T and small t. So when you see a T, you have to look closer to see whether it's tablespoons or teaspoons. Now, we said that volume and capacity here are really just 2 different ways of measuring the same thing. They're measuring how big something is, or how much it holds. So it makes sense that there should be some sort of a conversion between them. However, there was not. They developed totally independently. So the conversions are pretty approximate. 1 gallon is approximately 231 cubic inches. And 1 cubic foot is obviously bigger than a gallon. It's about 7.48 is closer, but for most of what we do, 7.5 gallons is close enough. So you can see there again, those conversions are just not very neat because the units were never intended to work together. So now let's get back to the metric system. We've mentioned it a few times. The metric system has an advantage. It is a planned system. The standard or customary system was what we called an evolved system. There was a need, we developed something, we evolved something to meet it. Over time, we had all these different things for measuring different items. We evolved them, we changed them to make them work together. Evolved sounds fancy, but it's not. It's really a bad thing. It made for a very messy system. The metric system was planned. Like we said, we had used standard measurement for hundreds of years. We knew what worked well and we knew what did not. So they kept the things that worked well and they changed the things that did not work well. The biggest thing that did not work well was all these different units for each type of measurement. So in the metric system, what they shot for was only one unit for each type of measurement. So for length, that unit was a meter. Abbreviated, just a small m. So this is a meter. Now, unfortunately, if I stop it right there at my finger, that's a yard. So a meter was just slightly bigger than a yard. Well, it's slightly bigger than a US yard. I can remember when I first learned the metric system thinking, why would they not just take the yard and use it as a meter? Would have made a lot more sense, would have made it a lot easier to convert between the two. Well, the metric system was developed in Switzerland. And in Switzerland, this actually is the Swiss yard. So they did make the meter equal to a yard, just not the US yard. You might ask, well, why not? Well, remember we said this was developed in the 1880s. A long time ago. Most of us think of it as way more modern than that, but it has been around for about 140 years. In the 1880s, the United States was not a world power. The United States did not really come on the world scene until World War I, maybe even into World War II. So around the 1920s was when the United States kind of established itself as a power in the world. Up until that point, especially in the 1880s, nobody cared about the U.S. So the U.S. yard was not used. For weight, they used a unit called a Newton, developed with a capital N, abbreviated with a capital N. The metric system tends to focus on mass, where the standard system or customary system focused on weight. The unit for mass was a gram. A gram is abbreviated with just a small g. But more importantly, it was planned. A gram is the mass of 1 cubic centimeter of water. Now, we haven't talked about the prefixes yet, but a centimeter is just a fraction of a meter. For capacity, we use the liter, abbreviated with just an L. I've always been taught to abbreviate with a capital L. I found out years later that wasn't necessary. The main reason I was taught to use a capital L is if you have something like this, is that 51 or is it 5 liters? Well, if you use a capital L, it's pretty clear that that's 5 liters. So that was the reason I was told to do that, but you don't have to use a capital L for it. Now, the liter was also planned out. Now, smaller than a liter, a milliliter is 1,000th of a liter, is defined to be equal to 1 cubic centimeter. So you can see we have these links from one unit to another. A milliliter is 1 cubic centimeter. So there's a direct link between capacity and volume. 1 gram is the mass of 1 milliliter or 1 cubic centimeter of water. Direct link between capacity, volume, and now mass as far as the mass of water. So this was very well planned out. And now all these units then, if we wanted to measure something smaller or larger, we use metric prefixes. Metric prefix deci meant 1/10. So a decimeter was 1/10 of a meter, deciliter was 1/10 of a liter, decigram was 1/10 of a gram. Now I'm laying this chart out in this direction for a very specific reason, and I'll show you in a second why when we look at conversions. Smaller than deci was centi. Centi was 1/100th. So a centimeter was 100th of a meter. Centigram was 100th of a gram. Then we had milli. Milli is 1/1000th. Again, millimeter, little m was millimeter, was 1,000th of a meter. dm was decimeter, 1/10 of a meter. cm, centimeter, 100th of a meter. Now after that, we stopped going every 10. We skipped 10,000 and 100,000, and we skipped to a millionth. A millionth was micro. Now, M was already used for milli, so we couldn't use mm for millimeter. So we used mu-m for milli. So mu is a Greek letter mu, looks like that. Looks like kind of like a U with a long front tail. It was, again, just so we didn't reuse letters in our abbreviations. Now, in the medical field, medicine was one of the first fields to have to keyboard everything into a computer. So there's no mu key on the computer. So in the medical field, they often use MC for micro. So MCM would be a micrometer, MCG would be microgram. Smaller yet, then if we went up to a billion, that would be nano. A nanometer is a billionth of a meter, extremely small. That's about the size of an atom. Most atoms are between 1 and 10 nanometers. So you used to hear a lot about nanoscience or nanotechnology. All that is talking about is things that are the size of an atom. They're looking at building technology from atomic level rather than from what we're used to. If I need something bigger than a meter or bigger than one of our standard units, deca. Deca was 10. Now, since dm was used for decimeter, dam was decameter, dal was decaliter, dag was decagram. And hecto meant 100. So hm was a hectometer, or 100 meters. Kilo was 1,000. Kilometer was 1,000 meters, kilogram, 1,000 grams, and so on. And again, we skip 10,000 and 100,000, and we go to mega, which is a million. So mega was abbreviated with a capital M. So capital M, little m was a megameter, or a million meters. Now, megagram is a million grams. 1 megagram is equal to 1,000 kilograms. Because the ton was so ingrained in the customary system, they developed a metric ton. So 1 megagram, there's 1,000 kilograms, was 1 metric ton. When you hear about world trade on the news, if you ever listen to the Farm Report or anything like that, where they talk about, wheat is now trading for so much a ton, they're talking about metric tons. So conversions within the metric system were very simple because each of these units here, if I go from one unit to the next, the size of the unit is either just being multiplied by 10 or divided by 10. And when you multiply or divide a number by 10, we just move the decimal point. So if I have something like 0.42 liters, and I want to know how many milliliters that is. Well, here's liters. I'm going to milliliters, which is going to be here, milli. To get from liters to milliliters, it's 1, 2, 3 spots to the right on my chart. So I take my decimal point and I move 1, 2. To move 3, I have to add a 0 spots to the right. So that's 420 milliliters. Or I might have 27,000 grams, and I want to know how many kilograms that is. Well, going from grams to kilograms, that's 1, 2, 3 spots to the left. So my decimal point starts there. I have to go 1, 2, 3 spots to the left. 2.7 kilograms. I'm sure you guys have all seen the metric system in your science classes, so I'm not going to spend a lot of time here today doing conversions. You guys know the moving of the decimal point and all that. I do want to take a couple minutes, though, to talk about converting between metric and standard. First of all, let's talk about the one that's done the most, and that is the weight to mass conversion. Like we said, the standard system tends to focus on weight. The metric system focuses on mass. So one conversion that's a little sloppy is the weight to mass conversion. 1 kilogram is what we tend to use for our mass in the metric system, is equal to about 2.2 pounds. It's actually 2.208 pounds. So if we have a patient, and most now of our medical dosages are based off of kilograms. So if I have a patient that comes in and reports that they weigh 180 pounds, we need to convert that into kilograms. And so we'll use our dimensional analysis tool. We take our 180 pounds and put it over 1. We're getting rid of pounds, so I'm going to put pounds on bottom, and we want to go to kilograms. And so then we can fill in, once we have the units in the correct places here, we can use our equivalency to fill in the numbers. 1 kilogram is 2.2 pounds. So 1 kilogram, 2.2 pounds. The pounds cancel out in our fractions. 180 times 1 kilogram is 180 kilograms. 1 times 2.2 is 2.2, and then we divide. 180 divided by 2.2 gives us 81.82 kilograms. We have our units of length. 1 inch is equal to 2.54 centimeters. So if we have a patient, again, that comes in at 6 foot 1 inch, or 73 inches, and we need to have them, let's do doing a body surface area calculation or other calculation, we need to have that in centimeters. So we'll put our 7 foot or 73 inches over 1, and again, we're getting rid of inches. Inches are on top, so we put it on bottom, so it cancels out. Our other unit is centimeters. Then we go to our equivalency. 1 inch is 2.54 centimeters. So 1 inch, 2.54 centimeters. The inches cancel out. 73 times 2.54 gives us 185.42 centimeters is the height of that patient. Now, the textbook gets a little carried away with this dimensional analysis. This is what it's really used for. We'll look at more of this on Friday. For right now, I'm going to have you in your book, page 103, 1 through 19, the odds. Page 110, 1 through 41, the odds. And page 118, 1 through 19, the odds. We will wrap up measurement on Friday, which means next Monday is going to be our Unit 2 test. Your people at each school should have the tests for you, so they'll be all ready to go for Monday. You will be able to use, just like Unit 1, you'll be able to use your notes and your books and your calculator. There is no requirement for showing work on this one. Although if you want partial credit, you should show your steps. So with that, you guys have a great day, and hopefully we'll see you all on Friday.